In this video, we're going to talk about alkanes, and specifically the property of alkanes. There are two videos in this part. There's the property of alkanes and the reactions of alkanes next. In this video, we're going to talk about what is an alkane, and remind you of that, and then go through the different properties in terms of melting point and look at some sigma electrons as well. So the first thing is just to remind you of the alkanes. So we've got alkanes here, we've got all our molecular formulas. I'm going to talk through a few of those properties of alkanes. So they're saturated, carbon-carbon single bonds only. Okay, if it's saturated, just those single bonds, specifically of carbon bonded to carbon. We have a general formula of CnH2n plus 2, and the name of it ends in ANE. So if we look over here and we can say, look, one carbon is meth, and then we end it in ANE. We're also applying our general formula down here, and we're doing CnH2n plus 2. Stop the video right now and check, and you'll see that all of those apply to CnH2n plus 2. Now, the last thing we want to talk about is free rotation around the carbon, and we'll describe that in a later slide. Now, that's not too important when it comes to alkanes, but it'll become really important when you start talking about alkenes, the comparison between alkanes and alkenes. So the shape of alkanes, just to remind you, pairs of electrons repel each other, okay, and when we draw the alkanes, we draw them with 4 bonds to each carbon. So the simplest alkane is going to be methane, and we put 1 as a wedge and 1 as a dash. So if you remember, the dash is going away from you and the wedge is coming towards you. We have a bond angle because of 4 bonding pairs that repel each other as far apart as possible of 109.5, which is called tetrahedral because of 4 faces. Now, let's go into sigma bonds in a bit more detail. You may have already heard of sigma bonds, but sigma bonds are essentially single bonds. So each one of these bonds is a sigma bond. And sigma bonds happen because they're a shared pair of electrons, covalent bond, and they happen through something called hybridization. Now, do not worry about the term hybridization. It's just overlapping of orbitals, and you don't need to know it in too much detail, but we include it here just so you understand where the term sigma comes from. Now, these sigma bonds, if we show you here, come from the pair of electrons that are in each part. So here you can see the single bonds of each one have a pair of electrons. Now, one of those electrons came from the hydrogen and one of it came from the carbon. The carbon's electrons are in p orbitals and the hydrogen's electrons are in s orbitals. Now, hopefully now you're starting to remember what the s and the p orbitals look like. Well, the s orbital looks like a sphere and the p orbital looks like a dumbbell. When they combine, they look like this. So what we can see here is we have the end of the dumbbell and the other part of the dumbbell just hidden behind here. Notice this end of the dumbbell is considerably larger. That's because the s orbital from the H has combined and overlapped with the p orbital, making this part larger. And you can see that there are 4 lobes. So 4 of these, so 4p, and that means you've got s and p overlapping with each other due to these different bonds. Now, with these different bonds, you can then see that around one of them, we're showing here that they rotate. What it means, it rotates like this. Okay, and then that's what we call free rotation. So these lobes will turn like that freely. Now that is how we talk about sigma bonds, but in simple terms, sigma bonds are just single bonds. So single bonds. For every single bond, we have 2 electrons. So common questions can be, how many sigma electrons are there? So what you've got to do is count the number of sigma bonds, and then to find out the number of sigma electrons, just times by 2. So we have gone over alkanes, and we've reminded you the names, the general formula, that they're saturated, carbon-carbon single bonds only, and talked about these sigma electrons. But how does the length of the hydrocarbon affect the boiling point? Now, this also works with melting point as well, but boiling point is the one we focus on for this exam. So the first thing is, with longer chains, there's more surface contact. We'll explain that in a second. And therefore, there are stronger induced dipole-dipole attractions. Now, these are also known as London dispersion forces. Either is fine. What I want to focus on is this word stronger. I often see many other words instead of stronger that don't quite hit the mark. So really, I'm leaving one word here, stronger. That is the word that gets you the mark. I'm not including all the other words you can use because I don't want to emphasize them. I'm emphasizing this, stronger. So stronger induced dipole attractions. Now, why, for example, does that work? So if we take a molecule, and you can see this is 1, 2, 3. So that is propane. And whether melting or boiling and things like that, you have to break the intermolecular forces between the molecules. So how can these line up? So these can line up like that. That's the closest they can be. And you can see there's contact from here all the way through to here. Now if I take another one, and I take a slightly longer one, okay, and if I count the carbons, 1, 2, 3, 4, 5, 6, okay, so I've got hexane. I take another hexane and line it up, and let's do that there, and I've lined that up. Now I've lined it as close as I can get the two together just to emphasize the point. Then you can see, look at all that surface that is close to each other. So you can get more surface contact, and obviously with London dispersion forces, the more electrons you have, the stronger those London dispersion forces, and with the higher surface contact that we have with these alkanes, you will get those stronger attractions. Now those stronger attractions lead to the fact that it takes more energy to break those forces, and so melting and boiling point will increase. But you'll mainly be asked about melting point in your exam. We're now going to move on to looking at how the branching affects the boiling point. Now, the branching means that there is less surface contact. So if we have something that's branched, it will have less surface contact with other molecules. That results in weaker London dispersion forces. Okay, and remember you can call it induced dipole-dipole. Now, if we look at two examples, so we're going to look at methyl butane. So methyl butane is that. So we've got methyl at position number 2. Really, we should call it 2-methyl butane, but let's not worry about that. And you've got 1, 2, 3, 4 carbons. If we draw an isomer of that has exactly the same molecular mass, and then we compare the boiling points, we can see this in action. So therefore, we go for butane. So we've got butane, we've got methyl propane. Let's look at the surface contact. So if I want to line two of these molecules up, and I encourage you to do this yourself, okay, and you can line two of them up there. Now, if we do exactly the same on this one, and you can see, look at that, all that surface contact, loads of surface contact. Look at this tiny amount of surface contact. So it's less surface contact in the branched version than there is in the straight chain. Now, if that's the case, that actually affects their boiling point. Now, butane is 273 Kelvin. Where it's come to methyl propane, that is 261 Kelvin. So you can see the boiling point has reduced. It takes less energy to break these intermolecular forces, these London dispersion forces, because there is a lower surface contact between them. So this lower boiling point, as a result of that, is because of the difference in these London dispersion forces, even though that molecular mass is identical.